a Laplace transform is simply an improper integral. What it does and the applications of it is most useful for us in mathematics, engineering, science, and physics. And to me, it's erroneous to say mathematics and physics because they're the same. But because of the philosophy of the day, everything is broken into its parts nowadays. What the transform is doing is that it has its own set of criteria. It becomes its own world, basically. It becomes its own definitions, own properties, axioms, which are so different from what you've seen before from anything else. It's its own classification. It's its own study. And what it seeks to do is to, one, solve a differential equation, but secondly, to solve difficult integrals, improper integrals. If you have circuits that tend to go into infinity, where there's no time limit, or if there's a time delay, then Laplace transforms are most useful in those applications. What we will try to do in the next 4 sections is to try to build all the properties for the Laplace transform. And then what we'll do is to take a differential equation that we've solved from before, any differential equation, and then apply the Laplace transform to it and be able to solve that differential equation. And so hopefully at the end of this, and you'll see that we've talked about several different ways of how to solve a differential equation. And so you can add this to the last of that list for this particular course. There's a chapter after this that talks about systems of differential equation, and the way we solve those is basically using the eigenvalues and eigenvectors from linear algebra. And if you know that, then chapter 8 is nothing. It's just plug in and you get the answer. If we have time, I can go there and take one section out of chapter 8 and look at that in terms of solving systems of differential equations using the eigenvalue and eigenvector, and it's very easy. But today and for this week and next week, we will consider the Laplace transform. So, and today in particular, we want to establish the definition for the Laplace transform, and to be able to, one, get the Laplace transform by definition, which takes a while. But I want to cover that, and I want you to see it, because after you do that, then when you're having to work a problem, you appreciate the problem, because solving by definition just takes a long time. But it's good because when you do that and you spend time with it, it becomes a part of you. The second part of this section in 7.1 is, first we will deal with the definition, show how we can get all of the transforms by the definition. We'll look at the theorem 7.11, and they'll list various transforms. We want to be able to show that what's in the theory can be found by actually computing that improper integral in the definition for the Laplace transform. And then from there, we'll just solve problems, basic problems, using the theorem, which should be a whole lot easier then. Okay? But I want to show you where everything comes from. Quite naturally, on the test, the first problem that I have is to solve this Laplace transform by definition, right? And hopefully you've deduced how we do things here. That I'm not going to just cover something in class and just say, oh, we were just playing on that. You no need to know that for anything. Well, yeah, you got to know this stuff. It's most important. Let's see. So here's a definition for the Laplace transform. Let f be some function defined for t positive, or possibly even 0. Then the integral, we denote this as the Laplace transform. That L represents the Laplace transform. That special bracket of the function, f, is equal to the integral from 0 to infinity of e to the negative st, which is standard for the Laplace transform, times the given function f of t dt. And then from there, we have to integrate. And if the integral exists, then we say that the Laplace transform exists. And the existence of the integral, since we have to integrate with respect to a limit, we talk about the integral being convergent. Right? And so we'll show convergence and show you that little s is important, because that s will determine convergence. If s goes one way, we get convergence. If s goes a different way, we get divergence. So where's the breaking point? If this was in psychology, we'll look at the mental breaking point for a person. At what point in their life did things go haywire? And so that S will determine for us a breaking point, whether it's psychology. If it's economics, we also deal with the economic market in terms of where did we start having profit based on the revenue. And so that little s in economics is most important for the study there. Here's the beauty of all this, people. Just because people are studying the STEM subjects, like science and technology and engineering and mathematics, and we think that, okay, I have to know math and calculus. Let me tell you, you get beyond that and you start working on your master's and your doctorate, whether it's in economics or psychology, and guess what? They have to know calculus too. And a whole lot of it. I had a friend when I was in grad school, he was working on his doctorate in political economy. And I was in grad school studying theoretical and applied mathematics in Pittsburgh, and he was looking at about the comparable amount of mathematics that I was dealing with up at Pitt, and he would call me, and he was at Stony Brook in New York. He would call me sometime, and he said, "Hey man, if I knew that I was going to be a mathematician, I would have changed my major a long time ago." I said, "Man, that's interesting." But the thing that is good for us, and my point is that mathematics runs the whole world, and without it, you can do nothing, no matter what discipline you're in. Now, the theory of the transforms, here we list 7 transforms. We're going to show these, and I'll show most of them today here in class. And then they have some problems where they say solve by definition. The definition is up here. We're going to solve by integrating. If they don't say to solve by definition, then we just use the theorem and just plug in what the answer is going to be, and that's a whole lot easy. Okay, so let's begin. Objective: use the definition of Laplace transform to verify the transforms here in theorem 7.11. So I begin there. We take the first one, and I'm going to label them as 1, 2, and 3, because this part B has like maybe 4 guys in there that I want to look at, so I can show you that pattern. So we'll show that the Laplace transform of 1 is equal to 1 over s. And s is some fixed number. X is some fixed number. So we start and show, and here, this is by definition. So the Laplace transform of 1, by definition, is the improper integral from 0 to infinity. It's the 1 times e to the negative st dt. Now back in calculus, and I'll write it as such, we would rewrite this as the limit as b, and I'm going to use the Larson notation, as b goes to infinity of the integral from 0 to b e to the negative st dt. Do you remember that notation? Okay. So we integrate so we get the limit as b goes to infinity of, let's put that in brackets, negative 1 over s times e to the negative st. We integrate that from 0 to b. You understand with that, the integral of e to the negative st, you have to use a u du substitution, right? Let u equal to negative st, and du is negative s dt, right? I think I can put it here. So dt is negative 1 over s du. So the dt here is replaced with the negative 1 over s du. So we have, that's the limit b goes to infinity. This is negative 1 over s times the integral of e to the u du. And so we get the limit as b goes to infinity of negative 1 over s times e to the u. Evaluate that from 0 to b. So that's why we get the limit here as b goes to infinity of negative 1 over s times e to the u, where u is the negative st. Evaluate that from 0 to b. Okay. And so we plug that information in. This is the limit as b goes to infinity. The t is the term that's being transferred here. So this is negative 1 over s. Again, s is a fixed number. This is e to the negative sb. And then we evaluate at 0. So this becomes negative. This negative is plus 1 over s times e to the 0. Now, this e to the negative sb, if s is positive, then that e to the negative sb, as b goes over positive terms, that term goes down to the denominator. So here, let s be a positive term, and so that gives us the limit as b goes to infinity of negative 1 over s times e to the sb, and this is just plus 1 over s. What is the limit? What is the limit of 1 over e to the sb? S is fixed, so it has no strong bearing here. B is going to infinity. So what's the limit of this first term? 0. All right. What's the limit of 1 over s as b goes to infinity? 1 over s, because 1 over s is fixed, right? So 1 over s just becomes a number. It's a constant. So the limit of a constant is a constant. And so, yes, all we have is just 1 over s. So we started with looking for the Laplace transform of 1. Now, secondly, the transform of t. This is said to be the improper integral from 0 to infinity of t times e to the negative st dt. So we write this as the limit as b goes to infinity. Hadn't integrated yet. Of the integral from 0 to b, t times e to the negative st dt. So we use integration by parts to integrate that. And for me, I found it easier to use the tabular method, which is the shortcut for integration by parts. So we take the t, the first term, we differentiate that, we get 1. Differentiate the 1, we get 0. Alternate the signs, plus, negative, plus. We take the other term in the integrand, e to the negative st. We write the first term, we just write the term, e to the negative st. And then we integrate on that side, right? So what's the integral of e to the negative st? Right, we just found that up in number 1, right? So negative 1 over s times e to the negative st. And you know the solution is slanted. Well, that 0 times whatever, we don't care, but here we have to integrate this guy one more time, right? So what's the next integral? When you integrate negative 1 over s times e to the negative st, what do you get? You know, just quick, the integrals of these guys is the same term always times negative 1 over s, right? So negative 1 over s times negative 1 over s is positive 1 over s squared, not negative, right? So it's 1 over s squared times e to the negative st. The next one would be negative 1 over s cubed times e to the negative st. The next one is positive 1 over s to the fourth times e to the negative st, and on and on and on. Right? So, Mr. Tyler, I was trying to listen out for the positive, not the negative. Too many people in the world, my friends, are in the negative. Too many people, their minds are negative. Their language, you don't want me to preach. Their language is negative. You know, I want to be around people who are positive. You got negative folk around, and it seems like everything they talk about and think about is negative. You know, I was talking to a fellow, he was so negative. I said, well, maybe I can tell him something to, you know, try to cheer him up and make him think positive. And so my friend had a dog, and my friend said, I want you to check out my dog. And so this negative guy said, what kind of dog is it? He said, man, my dog can walk on water. And so the guy said, man, nobody can walk on water. Apparently he hadn't been reading his Bible. But anyway, so the fella said, let me see your dog, you know, walk on water. So they were out there in the fishing pond, and he told little Raffy to go sick him. And sure enough, little Raffy, he started to run on water. And so the fella, who was a cool guy, he looked at the negative guy and said, hey, what you got to say about that? Hoping he'll say something positive. And so the negative guy said, I bet you that dog can't even swim. He walking on water. He can't swim. I said, Lord have mercy. Anyway, well, we want to stay in the positive. So this is 1 over s squared times e to the negative st. And we don't care about the other one because that's 0 times whatever, and that's no bearing on us. And so now this becomes the limit as b goes to infinity. And so the integral here just becomes these terms here. So this is negative t over s times e to the negative st. And then this is minus 1 over s squared times e to the negative st, and we close that up, and we evaluate the t from 0 to b. So we started with the Laplace transform of t, and so this is the limit as b goes to infinity. We replace here, for the evaluation of b, we replace the t with b, so this is negative b over s times e to the negative sb minus 1 over s squared times e to the negative sb. Now we evaluate the t at 0, so this becomes minus, that's plus 0, minus this minus becomes plus, and this is 1 over s squared. The first term was 0 because this is just t, right? And so if t is 0, that whole term is 0 there. So then we come here, minus this minus is plus 1 over s squared times e to the 0. Okay. See if I can write this out one more step. I was thinking about it before I wrote the other stuff. So this is negative b over s times e to the sb minus 1 over s squared times e to the sb, and this is plus 1 over s squared. Now, so What's the limit of negative b over s times e to the sb? What's that limit? We don't know. How do you know that? Okay, so if they both have infinity, so are you saying that infinity divided by infinity just cancels out? Huh? To 1? Where'd you get that from? Infinity is not a number, right? If it was 6 divided by 6, of course that's 1. What's 0 divided by 0? Is that 1 too? So what about infinity divided by infinity? You said it was 1. Oh, man, what is this, political science? I was a Democrat, now I'm a Republican, now I'm an independent. Whoa, you know. This is math, folks. It does not govern itself on popular opinion. Oh, mercy. Well, maybe that first one was too hard. Let's go to the second one. Maybe it's a little bit easier. So what about this right here? This is one. Remember, the s is just fixed, right? So s is fixed. Think about s as a number. B is a functional term. It's the values are going from 1 or 0 to infinity. So here, this is 1 over s squared, and down here is e to the sb. So what happens to that as b goes to infinity? That goes to 0. Right? What about the limit of 1 over s squared? That stays, because this is a constant. The limit of a constant is a constant. So this guy is just 1 over s squared. All right? So for that first term, if you look at it and think about it, it looks like it's negative infinity over infinity. Right? It's negative infinity, right? Because b is going to infinity times a negative. That's negative infinity, right? And then you get e to the sb as b goes to infinity. E to the infinity goes to infinity a whole lot quicker. So I get negative infinity over infinity. What is that called? Hmm? I mean, but how do you get it? How do you get 0? I see what you're saying. That does make sense. Yes. Okay. There was something that you had in calculus that we talked about this particular phenomenon. What's this phenomenon called? When I get 0 divided by 0, when I get infinity divided by infinity, when I get 1 to infinity divided by 0, when I get infinity raised to the infinity power. What was that called? I don't hear none on this side over here. Let me go on this side over here. What is that called? Huh? Well, that's what you talked about back in like the 5th grade, right? You know, that was a 5th grade term. This is college, guys. We moved up like the Jeffersons, you know? So. Right. Okay, that's what we're getting to. But why do you use L'Hopital? If you have a rough crowd. Indeterminate form. Do y'all remember that phrase? Oh. Like my son. Oh, yeah, right. If you have an indeterminate form, then we can apply L'Hopital and take the derivative of the numerator divided by the derivative of the denominator. 0 divided by 0 is an indeterminate form. You don't know what it is. It's indeterminate. Infinity divided by infinity could be anything, right? It's indeterminate. So anytime you have indeterminate form, back in calculus, especially in calculus 1, we said that possibly you have 2 possibilities you can do. You can either factor or you can rationalize. And then in Calculus 2, we got more sophisticated and said, look, you can do something a whole lot easier. You can apply L'Hopital's rule. Get the same thing. So here we have infinity, or negative infinity divided by infinity. That's an indeterminate form. So the first term is negative infinity over infinity. We call that it's the indeterminate form, right? If it's indeterminate, then we use or apply L'Hopital's rule. So here, this is the limit as b goes to infinity. The derivative of negative b is negative 1. This is all over. The derivative of e to the sb is the derivative of sb times e to the sb. Well, the derivative of sb would be s times 1. So this is going to be s squared times e to the sb. Close that up. We know we have a fixed constant here, 1 over s squared. Well, that's a 2 there. So now, what is the limit of negative 1 over e to the sb as b goes to infinity? 0. So when you say that the answer is something, you got to have a reason why, a mathematical reason, that is, mathematical reason why. You need to be able to know why. If not, then the higher you go up, you're going to come across some other stuff. And if you don't know foundationally why this was and why that is, then when I get up there, then you make it messed up. So in mathematics, we want to make sure that we have a reason. Right? We have a reason. Now Tyler was on to something too, and where he was that this negative b over s times e to the sb. He was saying that as b goes to infinity, e to the sb, or e to the b, if you will, goes to infinity faster. And so if you look at that in terms of some type of trajectory, you can see where this would go to 0 in terms of analytics, and that makes sense. Here's the funny thing about that. The proof of L'Hopital's rule goes over that. But to be able to say that, Tyler, you would have to actually show the proof of that. Well, it's complicated. We just say indeterminate and just use L'Hopital's rule, right? He's proved it for us already. He got credit. His name is on the theorem, right? Well, in advanced calculus, we definitely have to prove all of those notions in very intricate detail. It's not complicated if you like that kind of stuff. So anyway, this just becomes 1 over s squared. Correct. And this was the Laplace transform of t. I'm going to do the next one. I'm going to look at the Laplace transform of t squared. Then I'm going to look at the Laplace transform of t to the third power. See if you see the pattern. If you see the pattern, then we can make a theory out of it, get a formula. All right? So again, just remember, we looked at the Laplace transform of t, and we got 1 over s squared. So now what happens with t squared? I think this is number 3. Okay, thank you. The Laplace transform of t squared. So this is the integral from 0 to infinity of t squared times e to the sb dt. We write this as the limit as b goes to infinity, the integral from 0 to b of t squared times e to the negative st dt. So we use the tabular method for integration by parts. We get t squared, 2t, 2, and 0. Alternate the signs. Then over here we integrate this e to the negative st. So that's negative 1 over s times e to the negative st. Integrate that, we get 1 over s squared times e to the negative st. Integrate that, because I think we'll need it. This is there. Yep, we need that one. So this is negative 1 over s cubed times e to the negative st. Okay. So if that's the case, then we have the limit as b goes to infinity of negative t squared over s times e to the negative st. Just put the combinations together. So negative t squared over s times e to the negative st. Then this is minus 2t over s squared times e to the negative st. And this is minus 2 over s to the third times e to the negative st. All right. You're gonna see these patterns over and over again, and I hope you conclude by saying here's one observation that you'll be able to see, that the Laplace transform, when you look at these limits, the Laplace transform is usually the tail. The answer would be the tail. Okay? You'll see it. If you look at the previous two examples, it was that tail end that was the limit of a constant that gave us the answer. Everything typically before that went out to 0. Right? All right, so here t is evaluated from 0 to b. Let's plug that in. It's the limit as b goes to infinity. So this is negative b squared over s times e to the sb minus 2b over s squared, 2b over s squared, and this is e to the sb, and this is minus 2 over s cubed times e to the sb. So now this becomes plus, we plug in t to equal 0, I get 0 squared, that's 0, plus 0 here, right? And then this is plus, you plug in t to equal 0, we get plus 2 over s to the third. Okay. Again, we go through the same argument that we went through the first one. This is negative infinity squared over infinity. Infinity over infinity. This is infinity over infinity. Right? Now this guy is a fixed number over infinity, right? So this goes to 0. Right? The first two terms we use L'Hopital's rule. And if you want to impress me on the test, this is fine by saying, applying L'Hopital's rule twice, we get 0. Just say that, and just put 0 there. I'm fine with that. If you understand what's going on, no sense of having to, keep writing this over and over again. Right? And I understand. Calculus, to courses like this and beyond, calculus becomes like 3rd, 4th grade math. Remember in 3rd, 4th grade math, you did like 100 multiplication tables, which I didn't, so because I wasn't so bright. But then, later on in high school, whatever, you just multiplied whatever, and you're done. You keep on going. You don't do like a million things. You get it. So. In calculus, when we had to do the L'Hopital's, where you had to show that each time, whatever. But nowadays, and when you go on to your 3rd and 4th year in college, and especially in graduate school, you communicate when you write it and say, this is, and you say what it is, and because of that, this result would be whatever, and just keep on going. So here, and I'll just do it. Colors that black. So we do L'Hopital, so this is negative 2b over, this becomes s squared times e to the sb minus 2, good thing is fixed number, over s to the 3rd times e to the sb, and this is plus the answer. As it is in mathematics, it's typical in life that you're trying to get to the answer, but it's a lot of B's in front of the answer, right? But anyway, it's crazy. There's a lot of stuff, Where's the B's, right? Negative 2b over e to the sb, right? There's B's there, right? So you got to get through that stuff, man, to be able to get to the answer, and that's typical in life as well. That second term is a fixed number over infinity, so this goes to 0. Again, you get here infinity over infinity, so we apply L'Hopital's again. Again, by making the statement, apply L'Hopital's rule twice, you get 0, and then just move on and claim the answer to be 2 over s to the 3rd, and I'm fine with that. So here, I get negative 2 all over s to the 3rd, taking the derivative of the top and the derivative of the bottom. Get that out of there because we're finished with the limit on that one. And so now you get a fixed number divided by infinity, so this goes to 0. And our answer is 2 over s to the 3rd. Right. I'm going to do one more in that family. And here I'll just jump to the answer because you see the pattern for the Laplace transform of t to the 3rd. And to be honest with you, you definitely see it when we do t to the 4th, but I won't go that far because I need to do the exponential one and also a sine or a cosine. This is the integral from 0 to infinity, t to the 3rd times e to the negative st dt. The limit as b goes to infinity, the integral from 0 to b, bless you, t to the third times e to the negative st dt. Again, we set up the tabular method. Over here we have e to the negative st, negative 1 over s times e to the negative st, 1 over s squared times e to the negative st, and negative 1 over s to the third times e to the negative st. I think I need one more. That goes there. This goes here. Yeah, we need this one. 1 over s to the fourth times e to the negative st. So this Laplace transform of t to the third is the limit as b goes to infinity of negative t to the third over s times e to the st minus 3t squared over s squared times e to the negative st minus 6t over s cubed times e to the st then minus 6 over s to the fourth times e to the st. They're being evaluated from 0 to b. So this is the limit as b goes to infinity of negative b to the third over s times e to the sb minus 3b to the second over s squared times e to the sb minus 6b over s to the third times e to the sb minus 6 over s to the fourth times e to the sb. And then that's for b. Plug in b to t to equal 0, then we get plus, this is 0, plus 0, plus 0, plus 6 over s to the 4th. All right, let's see what happens. Start here. 6 over infinity goes to 0. I get infinity over infinity here. This is like infinity squared over infinity, infinity cubed over infinity. So I'm going to make the statement, applying L'Hopital's rule 3 times, we get 0 for those first 3 times, okay? Not Hopital. All right. So we end up with that tail over there being our answer. So this is the Laplace transform of t to the third is equal to 6 over s to the fourth. Now let me see if I can show you this just to review now. We started out with the Laplace transform of t, and that gave us 1 over s squared. Then we had the Laplace transform of t to the second, and that gave us 2 over s to the third. Then we have the Laplace transform of t to the third, and that gave us 6 over s to the fourth. Do you see the pattern? Do you want to see the next one? The Laplace transform of t to the fourth is 24 over s to the fifth. Yes, the Laplace transform of t to the n looks like n factorial over s to the n plus 1. All right. Okay. So that's what that is. So that was number 4. Number 5. What about the Laplace transform of e to the at? Laplace transform of e to the at, and not the a-team. So this is the integral from 0 to infinity of e to the at. A is some number. This is times, by definition, e to the st dt. So this is the integral from 0 to infinity of e to the a minus s times t dt. Now let's see if I can graduate you up to where I am, because I don't really write the limit b goes to infinity. I just leave it just the way it is. And so that's how the big boys do it. So you integrate this e to the a minus s in parentheses times t, and what that gives you is 1 over a minus s times e to the a minus st. That's evaluated from 0 to infinity. And that equals 1 over a minus s times e to the a minus st, with here t goes to infinity. Then this is, when you evaluate it at 0, we get negative 1 over a minus s, and you plug in e to the a minus s times 0. Now, that first term where you have it's 1 over a minus s, this is just a number, times e to the a minus s times t. You want this e, or you want the exponent, you prefer that if it was negative. Because if it's negative, then it drops downstairs, and then I have 1 over basically infinity. Right? Otherwise, you have e to the infinite term, and so it just blows up and it diverges. So we want to try to find out, where does it converge? Convergence based on s. Again, s is said to be the so-called breaking point. So if a minus s is negative, then I have a negative number times t, and t is going to over positive terms to infinity, right? So I put the restriction, let a minus s be less than 0. And then that would give us this first term going to 0. Do you see that? If a minus s is negative, then this guy just jumps downstairs and is 1 over e to the a minus st, and that fraction would go to 0. So we make that restriction. So here we say for convergence, let a minus s be less than 0. It's negative. Well, I know I just said we don't like to deal with negative folk. Well, it's okay. Because if something is negative, it just depends on the proper perspective of how you look at it, right? This implies, just add s to both sides. This implies that s is greater than a. So if s is a number bigger than a, then a minus s would always be negative. Right? That would guarantee convergence. So if that's the case, if that guarantees convergence, then this term right here, what is that? This term goes to 0. I have left with the answer, the tail. And that is this: the Laplace transform of e to the at is equal to this negative 1 over a minus s. You can distribute the 1 through the denominator, and you get 1 over s minus a. Okay. Now, for right now, let me just state the other terms in the theorem. This is number 6. The Laplace transform. My time is running out. I want to work just maybe 2 or 3 problems in the book. The cosine of kt, the Laplace transform, it was within me to work this out, but that'll take us 10 minutes. And so this is equal to s over s squared plus kt. Number 7, the Laplace transform of sine kt is equal to k all over s squared plus kt. Number 8, the Laplace transform of hyperbolic cosine kt. It looks like its counterpart for cosine, just the plus sign downstairs becomes a negative. So this is s over s squared minus k squared. If I was saying kt, I'm sorry. But s squared minus k squared. And then number 9, the last one that I have, is hyperbolic sine kt. And it's k over s squared minus kt. All right? Well, let's look at a problem, because now the one that possibly tomorrow when I come back, I will solve either 6 or 7. And so you'll be able to see that. Here, use the definition to find the Laplace transform. Let's take number 11. Now, when they say the definition, they mean to use that integral. So, Laplace transform of e to the t plus 7. This is the integral from 0 to infinity of e to the t. You can think about that as being, this is also times e to the 7, then times e to the negative st dt. Now, e to the 7th, I did that because e to the 7th is just a fixed number. It's a constant, so you put that in the front of the integral. This is e to the 7 times integral from 0 to infinity of e to the 1 minus s times t dt, right? e to the t times e to the negative st. You can write that as e to the parentheses 1 minus s times t. All right. We integrate that. We get this e to the 7th over 1 minus s. Again, use u du substitution times e to the 1 minus st. I'm going to graduate you up to where how I do the integral. And so this is, evaluate this at infinity. This is e to the 1 minus st. T goes to infinity. Then you evaluate this at the 0. So this is minus e to the 7th over 1 minus s times e to the 0. Now, how can we get this e to the 1 minus st to go downstairs so that I can have e to the 7th, which is a fixed number, over infinity? You need to make 1 minus s less than 0, and that'll give you s greater than 1. If s is greater than 1, then we get 1 minus s negative, so then that'll jump downstairs, and so then you have a fixed number divided by infinity, and we'll get convergence. So good. So we say here, let s be greater than 1. That implies that this e to the 7th over 1 minus s times e to the 1 minus st, as t goes to infinity, that guy goes to 0. So my answer is just that last term, that tail over there. So we say the Laplace transform of e to the t plus 7 is equal to, see if I can write it like this. This is e to the 7th over s minus 1. I distributed that negative through the denominator, right? So it becomes a negative 1, a positive s. And for the Laplace transform, they just like that s being written first anyway. Okay. That was number 11. Number 13. I reckon I'll conclude it at 13 for today. Laplace transform, what is this? Of t times e to the 4t. So this is the integral from 0 to infinity of t times e to the 4t. Remember, the Laplace transform by definition has automatically an e to the negative st in the integrand dt. Well, this is the integral from 0 to infinity of t times e to the 4 minus s times t. Four minus s times t dt. Well, I don't know if you like my notation, so we'll go back here and write it like this then. The limit b goes to infinity, the integral from 0 to b of t times e to the 4 minus st dt. Integrate by parts. I use the tabular method. So this is t 1 0 plus negative plus. This is e to the 4 minus st. And so this becomes 1 over 4 minus s times e to that exponent, 1 over 4 minus s times e to the 4 minus st. And then this is, integrate again, this is 1 over 4 minus s to be squared times e to the 4 minus st. let's see, this goes there, that goes there, and then no more 0. So this is the limit as b goes to infinity of, we have t over 4 minus s times e to the 4 minus st, and this is minus, space is running out, minus e to the 4 minus st over 4 minus s squared. So we evaluate the t from 0 to b. So this is the limit as b goes to infinity of b times e to the 4 minus s b over 4 minus s minus e to the 4 minus s b over 4 minus s squared. And then we plug 0, so this is minus 0 for t, and then this is plus e to the 0 all over 4 minus s to be squared. Now, for the first two terms, to get that e to the b minus s, e to the 4 minus s times b down in your denominator, you want to restrict that s is going to be bigger than 4. And that'll give you negative terms right there. Same thing for this. So let s be greater than 4, and if that be the case, then you get 0 here and 0 there. Does everybody understand that? Okay. Because that big term, that exponential term, just jumps downstairs, and then you get, by all means, you have to do L'Hopital on that first one. So you got b over infinity, and once you take that derivative of the top and the bottom, then you'll get a constant number 1 divided by infinity, so that'll go to 0. And this term here will be just 1 over e to the 4 minus s times b, and as b goes to infinity, you get 0. And so, yeah, that's fine. Yeah, you can just state that, that I know that you know what you're doing, and just. That's fine. And so here, let me close this up. And so that gives us that last part. This is 1 over s minus 4 to be squared. Well, e to the 0 is 1. But that's 4 minus s to be squared. And I'm writing s minus 4 to be squared. Did the instructor make a mistake? Was there something wrong in his bat utility belt? Has Robin hit his head? We'll find out next time. So, I mean, what's the difference? Are they the same? Is s minus 4 to be squared the same as 4 minus s to be squared? There's quietness. So quiet you can hear a pin drop. They have never been this quiet before in their lives. Even when they were born, they've made up a whole lot of noise. Maybe I can write to their parents and tell them I know how to make them be quiet. Pull out a DE problem. Is that the same? 4 minus s squared or s minus 4 squared? It's the same. Because 4 minus s squared is 16 minus 8s plus s squared, right? And then s minus 4 squared is s squared minus 8s plus 16. It's the same. I told you we like to write the S first for the Laplace transform. Okay. Thank you. You may go now. You don't want to leave me, man. I love this class. Come on to my house and help me cut the grass.